Yo, 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 what's up? It's me, I'm here bringing you some information about those sound waves. All right, so I just manipulated my sound waves in a lot of different ways to help emphasize that obviously we ourselves can change sound so easily, but also we can use instruments to do that. And we know throughout our daily lives that sound is different from different things in different places, and so let's dig into that. Well, you're going to need a science notebook page where we defined sound waves. We show the type of wave it is. We show what happens when we change our pitch and what happens when we change volume. So if we dig in here, we're going to start by looking at sound waves. Sound waves travel as longitudinal waves. And so the best way to think about this is that if you had a slinky that was just sitting on a table and you stretched it out on a table, you tap one end of that slinky, so let's say this is your hand, and you kind of just push on the slinky in this direction. The slinky will transfer its energy in this direction, where little parts will actually group together, and then other parts will be spread out, other spots will be grouped together, other spots will be spread out. And so what that looks like is, you can imagine that if this were the slinky, and it's best to draw longitudinal waves in this way, I've found, is if you draw these loops here that look like a telephone cord, if you've ever seen one of those, or like a slinky that's laid out on the table, and then you go back through, and the areas where I have all my arrows bunched together, I'm going to draw a bunch of these lines that will then show that essentially all these parts of the slinky are all bunched together. And so it'll happen again over here where I just stack these on top of the line. And so overall what I'm getting is that the energy is transferred through the slinky in a longitudinal way, meaning like left to right. So it doesn't go up and down, it just goes kind of left to right, and you can kind of see that effect. So it's kind of like this air molecule bumps into the next one, which bumps into the next one, which then transfers energy to the next one, and then this one moves forward. So you can think these are all air molecules just kind of vibrating in the air. When somebody opens up their mouth and starts screaming, that's their tongue, and this is their teeth. That's their lip and their nose. That's their eye. They scream, that energy gets transferred through the air molecules, and it comes on over here to my ear. That's my ear. Yep. And so then I can hear what they're saying. All right, well, what this means then is that since the motion of the wave is going to be parallel to the point of propagation. The point of propagation is, we'll go ahead and abbreviate that as POP. So this would be the point of propagation, or the person here would be the point of propagation. So the energy travels parallel to the point of propagation. So the energy is traveling parallel to where it was propagated from. So it makes it a longitudinal wave. But we can change those waves quite a bit by changing the different attributes of the wave. And so if we want to change the pitch of a noise, we need to change the wavelength of the wave. So the wavelength, if I were to draw something with a long wavelength, there's my crest, there's my trough, and there's my next crest. So this one has a wavelength that I'm going to call a long wavelength. And a long wavelength is going to create a low pitch noise. And if I change the wavelength to being much smaller, the frequency here is a lot, because there's a lot of waves happening in this period of time compared to the one on the left. But this wavelength is much shorter. So let's say that this is a short wavelength. And a short wavelength is going to make a high pitch noise. That was tough, but got it out. A high pitch noise. So again, let's just review. The wavelength is from crest to crest, or it could be from trough to trough. Here, if I go crest to crest, you can see the one on the left, I have a much longer wavelength than I do over with a high pitch noise with a shorter wavelength. Okay, so that's how you change the pitch, is by changing the wavelength. What about volume? How do we change the volume? If I want to change volume, I put a lot of effort into my voice. Well, that effort that we would say from our human body is actually going to be changing the amplitude of the waves that come out of our mouth. So the amplitude of the wave is going to change. So first let's draw a wave with a very small amplitude. Okay, that's a decent wave. And that one's going to have a small amplitude. And if it has a small amplitude, then it's going to be like a whisper. So I'll write that this is a quiet noise. That's a quiet wave. But if I wanted to increase the volume, because you can't hear me, what I would have to do is I would have to increase the amplitude. Now please note that I'm not changing the wavelength. The length of the wave from crest to crest is about the same. It's just the height that the wave is traveling. So now we have, in the green here, we have we'll call it a high amplitude. And this is a loud noise. There you go. So if you change the amplitude, you're going to end up changing the volume. So you can imagine musicians do this all the time as they sing and play music, that they're always changing the amplitude and the wavelength of the noises that they're making. You can even think about like a guitar. When you tighten the strings on a guitar, you're changing the amount that it's able to move back and forth and vibrate, which changes the wavelength. And as you strum it harder and harder, you end up changing the volume, or softer and softer. So it's, it's definitely related to music. So let's keep going though. Let's learn now about light. I'll see you in the next video. See ya.